Okay, so 6.1, the Laplace transform. So for many people, this is like the purpose that you take this course, okay, because you use the Laplace transform a lot in engineering. So first, we're just going to discuss the Laplace transform, and then once we have it down and we are able to use it, then we're going to explain how it works to help you solve a differential equation. Okay, so it's going to seem like this is just a stupid thing, but it really has a good application for solving differential equations. So the Laplace transform transforms one function into another via an integral. So it's actually itself a function whose inputs and outputs are both functions. So the main idea behind the Laplace transform is to determine how similar a given function y of t is to a standard exponential function e to the st. Now you might notice that e to the st is a common solution in differential equations, so that's why we use e to the st. So we determine the similarity by computing an integral. So there are lots of ways that I could tell how much alike y of t and e to the st are. One way would be to subtract the two. The closer you get to 0, the more alike they are. One way would be to take the ratio of the two. The closer the ratio is to 1, the more alike they are. Another way is to take the integral from 0 to infinity of the product of the two. Right. This is a way to tell how similar y of t and e to the st are, how close to each other they are. Right. We're going to get there. I haven't said it yet. So how does this integral compare y of t to e to the st? Let's do an example and see if the results illuminate how to do the comparison. So to find the Laplace transform of e to the 2t, we take the integral from 0 to infinity of y of t, I'll just write the whole thing out, times e to the negative st dt. And in this case, y of t is e to the 2t. That's how I've defined the Laplace transform. This is the integral that I do to see how close y of t is to e to the st. So obviously, when s is -2, my function y of t is going to be the same as e to the st. Does that make sense? So I don't really actually have to do the integral in this case to see how to make them the same, right? So if I want to compare e to the 2t to e to the st, just make s2, right? Kind of obvs, right? But we're going to do the Laplace transform just to get the same result with a simple problem. Okay, so replace y of t with an e to the 2t. Okay, so to simplify the integrand, those are like bases. I can combine them by adding the exponents so that I just have one term, and that's easier. So this is going to be e to the 2 minus s t dt. All right, so what is the antiderivative of e to the 2 minus s t? Over, yeah. It's a reverse of the chain rule, yeah. So I have e to the 2 minus s t. But if I were to take the derivative of this to go backwards, the chain rule would say multiply by 2 minus s. So I put a 1 over 2 minus s in front so that it'll cancel. And then evaluate that from 0 to infinity. And then who remembers how to take an integral from 0 to infinity? It's an improper integral. Yeah, replace with a b, yeah. So we take the limit as b goes to infinity of 1 over 2 minus s times e to the 2 minus s t evaluated from 0 to b. Okay, so then we plug in the b and we plug in the 0, carrying this limit along. When you're comfortable, you don't have to write down every single step, but to review, just going to do everything out. Limit as b goes to infinity. So I've got, actually, the 1 over 2 minus s is a constant. I can pull that right out of the limit. So now when I plug in a b, I get e to the 2 minus s b, and then plug in 0, and I get e to the 2 minus s times 0. All right, what happens as b goes to infinity to this first term, 2 minus e to the 2 minus s times b? It's going to depend on s. So I have two cases. What if s is smaller than 2? Goes to infinity. And if s is bigger than 2, it goes to 0. Okay, so it doesn't do anything, right? So this could be infinity or 0. This is if b is, not b, s. If s is less than 2, and this is if s is greater than 2. And this is going to be e to the 0, right? So it's minus 1. So I'm either going to have infinity minus 1, which is still infinity, or 0 minus 1, which is negative 1. So I have two possibilities here. 1 over one over 2 minus s times infinity minus 1, or 1 over 2 minus s times negative 1, 0 minus 1. And this one is if s is less than 2, and this one is if s is greater than 2. And this one that goes to infinity, it doesn't really give us much information. So we just write down this one. We say it's going to be, oop, I meant to write an s, not infinity there. So this is going to end up being 1 over s minus 2 if s is bigger than 2. So we only end up writing down the final function that converges. We only write it down for values of s that make it converge. So this is the Laplace transform of e to the 2t. So sort of what you said, when s equals 2 is kind of a special case. It's the special case that takes you from convergence to non-convergence, the bifurcation. That bifurcation is when y of t and e to the st are the same. So that's what it says here. When s equals 2, the integral becomes unbounded. The unboundedness tells us that y of t, which is e to the 2t, is identical to e to the st when s is 2. Okay, so we could have said that from the outset, but we're starting with a baby example. So it's the unboundedness, the value at which the integral becomes infinite. Okay, so the notation we use for the Laplace transform is a cursive L. So I would write the Laplace transform of e to the 2t, which I just calculated, was 1 over s minus 2. S minus 2. You write it like that. What? Yes. Thank you. It's an L. L for Laplace. No, it's just an L. Okay, so in order to be certain that the integral will converge for some values of s, because that is the Laplace transform, is the where it actually converges, we can only apply this transform to continuous or piecewise continuous functions whose growth is no faster than exponential. Okay, because when I did my calculation of the improper integral, this piece that it goes to infinity or it goes to 0, it has to go to 0 sometimes. If it doesn't, then you're not going to ever get convergence. So the way we can ensure that it goes to 0 is if we say it's the growth of whatever function I'm given can't be any faster than exponential. Yeah, they're not common functions that we use a lot. Yeah. Like you can't have a vertical function. Well, that's not a function anyway. No, that's not exponential, and that actually would be faster than exponential. I don't. It doesn't have a name. X to the x. Yeah. So this is sort of like the formal mathematical way that we say it can't grow faster than an exponential. We say that this function has to always be slower, has to always be less than some exponential eventually. So this says for t is greater than some value k. So if you go farther out and far enough out in your t values, eventually some exponential function will outgrow your function. It's not a very stringent, like you said, we don't have many functions that grow faster than exponentials. All right, so let's do this in general for any exponential function. Compute the Laplace transform. Y equals e to the AT. So I'm going to take the Laplace transform of e to the AT. That is the integral from 0 to infinity of my function y of t times e to the negative st dt. So this is just my generic formula. Then replace the y of t with e to the AT. So this is really going to nearly repeat exactly the example we just did. It's just that we had a 2 instead of an a. So it's almost the exact same calculations. Integral from 0 to infinity of e to the a minus st dt. So my antiderivative would be 1 over a minus s times e to the a minus s t, evaluate from 0 to infinity. So the way we evaluate from 0 to infinity is we evaluate from 0 to b, some value b, and then let b go to infinity. So I'm going to take the 1 over a minus s out. Limit as b goes to infinity of e to the a minus s t, evaluated from 0 to b. So when I plug in a b, I get e to the a minus s b minus e to the a minus s times 0. And then as b goes to infinity, e to the a minus s times b will either go to 0 or to infinity. So it goes to infinity if s is less than a, and to 0 if s is bigger than a. And this one is going to be, go to 1. So my final one is going to be 1 over s minus a because we forget about the case when it goes to infinity. I'm only interested in when it converges. So use the 0. So 1 over a minus s times -1 is 1 over s minus a. And this is if s is bigger than a. So there's your Laplace transform for e to the at. So now if you ever have to do an exponential, you don't have to do all the calculations out. No, I use the -1 to change the subtraction order. Yep. So we can use this for the case when a equals 0. Right? So my Laplace transform of e to the 0t, that's the Laplace transform of 1. So that would be 1 over s minus 0, right? Because a is 0. So this is 1 over s. Again, if s is, it was bigger than 0, right? Yeah. Sure. Just the end, or? Okay. Good? Okay. Okay, so we can take Laplace transforms. They're just integrals. It just changes one function into a different kind of looking function. A function in t changes to a function in s. All right, so now we're going to look at some properties of the Laplace transform. And these properties are what's going to make the transform useful in solving differential equations. So the first one is the most important one. It is taking the Laplace transform of a derivative. If you want to take the Laplace if you have a function y that has a Laplace transform L of y, the Laplace transform of dy dt is s times L of y minus y of 0. Look, that is kind of weird. Yeah. So, and it's kind of awesome too, because it takes a differential and turns it into just a linear, like algebra 1 problem, right? There's no more derivatives in there. Makes it a nice, easy algebraic problem instead of a differential equation. So let's see if we can show why this one is true, because it is unexpected. All right, so let's see. I want to take the Laplace transform of dy dt. So you will use the definition of the Laplace transform. That means take the integral from 0 to infinity of dy dt times e to the negative st dt. So I'm going to use integration by parts. We're going to let u be e to the negative st and dv be dy dt. dt. Yeah. So we choose u to be the e to the negative st and the rest of the integrand dy dt dt to be dv. So then du is going to be negative s e to the negative st dt. Just take the derivative of u. And v, if you integrate both sides of this, you get v equals y. So then we use, remember the whole thing about integration by parts is that the integral of u dv is equal to u times v minus the integral of v du. And if it has bounds, just throw the bounds on everything. So it's going to be 0 to infinity, evaluated from 0 to infinity, 0 to infinity. Okay, so u times v is going to be y of t, times v times e to the negative st That's u times v, evaluate that from 0 to infinity, minus the integral of v du. So I'm going to have negative s y e to the negative st dt. It is. It's awesome. All right, so let's see. We've got, well, we don't even have to do that. Let's pull out the s because it's a constant, and we have plus s integral 0 to infinity y e to the negative st. Y is a function in t. I should write it that way. So this is y of t. Yeah, that looks really similar to something, right? What is the integral from 0 to infinity of y of t e to the negative st dt? That's the definition of the Laplace transform of y. So I can replace that. This becomes plus L times the Laplace transform of y of t. And then this guy, now I'm going to use the fact that y can't grow faster than an exponential. Okay, so for s sufficiently large, so if y is growing as fast as it can, which would be exponentially, right? Then you've got exponential growth times exponential decay. These two are fighting. But if s is sufficiently big, this one will win because y of t is bounded by some exponential function. So just take an exponential that grows faster, and we can make this thing go to 0. So when I plug in infinity, this goes to 0, and when I plug in 0, so I have 0 minus y of 0. Well, s is a variable. Yeah, it's a parameter that we have full control over. Yeah, because we're trying to find the Laplace transform of something, and we say, well, it's this when s is something, and it's this when s is something. So we just say, okay, well, I can only make that converge when s is big, right? So we take s to be big because I'm really only interested in when it converges. So you just take whatever s you have to make it converge. Yeah. Yeah, so I'm just going to say this goes to this, and you can put a little note here for s sufficiently large. Like when I was doing this out early this morning, and that's exactly what I wrote in my notes. For s sufficiently large, I can do this. All right, so then I have 0. E to the 0 is 0, so I have 0. I'm sorry, e to the 0 is 1. So I have 0 minus y of 0 is negative y of 0. Plus L times the Laplace transform of y of t. And that equals my original thing, the Laplace transform of dy dt. So there's the property. It comes from the definition of the Laplace transform and some integration. Yeah. So that is a really nice property when you're trying to solve differential equations, because it can get rid of the differential part of the differential equation. And now you just have a regular old equation that we learned how to solve years ago. My other two properties are just linear properties. If you want to take the Laplace transform of f plus g, it's the Laplace transform of f plus the Laplace transform of g. And the Laplace transform of c times f is c times the Laplace transform of f. C is a constant. And these properties hold because those are well-known properties of integrals. And the Laplace transform is just an integral. All right, so now we're going to finally use a Laplace transform to solve a differential equation. We have this initial value problem. Qualitatively, and it's just a single differential equation, it's not a system. So I just made a slope field and sketched the particular function that goes through 0, 1, the initial condition. So it looks like I'm looking for a function y of t that as t goes to infinity, y of t goes to negative infinity. Just so I have some idea of what I'm looking for. All right, so we'll solve it. So we have dy dt equals y minus 4 e to the negative t. I'm going to take the Laplace transform of both sides. Equals the... Yes, we can solve this without a Laplace transform, yeah. But we're going to see that this is really nice and quick using the Laplace. All right, so the Laplace transform of dy dt, we just spent some time talking about what that is, and it's negative y of 0 plus s times the Laplace transform of the function we're looking for, y of t. And then I can use the other two properties of the Laplace transform that let me take these two separately. So I can take the Laplace transform of y minus 4 times the Laplace transform of e to the negative t. So I can take these two separately and I can pull the 4 outside because of the linear properties of the Laplace transform. All right, so remember that my unknown thing here, the thing I'm looking for is the function y of t. So in this equation, I can solve for the Laplace transform of y of t. That's going to be my unknown in this equation. And negative y of 0 I can replace. I know what y of 0 is because it's in my initial value problem. It's a 1. So I've got a 1, negative 1, plus s times the Laplace transform. I should use the square brackets like the book, of y equals the Laplace transform of y minus 4 times the Laplace transform of e to the negative t. Well, we know how to do the Laplace transform of any exponential. We did it earlier. It's 1 over s minus a. And in this case, a is negative 1. That was only when a equals 0. It was the... No, I can't because I have s Laplace of y and 1 Laplace of y. So I am going to solve for it. I'm going to put them together, but I can't just, they don't cancel. Yeah. So the Laplace of e to the negative t is 1 over s minus negative 1. Everybody remembers that that's the Laplace of e to the negative t. In the Laplace of e to the at is 1 over s minus a, and in this case, a is negative 1. All right, so now I'm going to gather all my Laplace of y's on one side, everything else on the other, just so I can solve for the Laplace of y. So I have s times the Laplace of y minus the Laplace of y equals 1 minus 4 over s plus 1. What do I do here? Factor out a Laplace of y. So I'm going to have s minus 1 times the Laplace of y. 1 minus 4 over s plus 1. Divide both sides by the coefficient on the Laplace of y, the s minus 1. So my final thing here is going to be that the Laplace of y equals 1 over s minus 1 minus 4 over s minus 1 s plus 1. Yes, this is s squared minus 1, but I'm going to leave it factored for now for reasons that we'll see soon. So remember, I'm trying to solve a differential equation whose unknown is a function y of t. So I'm partway to solving it. I now know what the Laplace of y of t is. I've got the Laplace transform. So I have to think of a function whose Laplace transform is this. I need a y of t such that the Laplace transform of y is 1 over s minus 1 Too complicated. Too complicated. Yes, because the Laplace transform is a linear operator. So yes, you can do each one separately. Sorry, I just want to write down every step here. So the inverse Laplace, right? To undo the Laplace, we have to have an inverse Laplace, because the Laplace transform is really a function. It's just that its inputs and outputs are functions instead of numbers. Okay, so we can have an inverse Laplace transform. And the inverse Laplace transform, just like the Laplace transform, has all the same properties, so that I can do them separately. So this is going to be the inverse Laplace of 1 over s minus 1. What? Minus the inverse Laplace of 4 over s minus 1 s plus 1. You can, but I'm going to leave it. You can do it either way. You could pull it out. Okay, so this guy, can you think of a function whose Laplace transform is 1 over s minus 1? Close. E to the minus t. Sorry, no, it's e to the t. It's e to the t. 1 over s minus a is the Laplace transform of e to the at. So this is e to the t. And then this one doesn't quite fit my, we only know one Laplace transform right now. We know the Laplace transform of e to the at. So if I could take that and manipulate it into looking like 1 over s minus a's. Yes, you got it, partial fractions. So I want to break this up into two separate fractions. Was it? I could call it -4, or I could just leave it as a subtraction. Doesn't matter. As long as I remember to put parentheses when I put this back in, it'll be fine. So did we remember how to do this? Yeah, multiply both sides of the equation by a common denominator, which is s minus 1, s plus 1. So when you multiply the left side, you just get a 4 because the whole things cancel. When you multiply the right side, Your s minus 1s will cancel with the a, and so you have a times s plus 1. And with the b's, the s plus 1s cancel, and you have b times s minus 1. And then we match up coefficients. So this says that 4 equals a plus b times s plus a minus b. So I have no s term on the left, which means that a plus b has to be 0. And my constant term on the left is 4, which means that a minus b has to be 4. The constant term from the right has to equal the constant term on the left. So a plus b is 0, a minus b is 4. Solve it. A is negative b, so negative b minus b is 4, and b is negative 2. So a is 2. A is 2 and b is negative 2. So this is all right, everybody got it? Yeah. So now we're much closer to writing these as things that look like something we know the Laplace transform of. What's the matter? No, b was negative and a was positive. B is negative 2. And then you plug in here, a is the opposite of b, so a is positive 2. Yeah, sorry. Yeah. Yes, so the negative 2, I just made a subtraction sign instead of plus a negative. All right, so we go back to the Laplace transform that we were just working on and replace 4 over s minus 1, s plus 1 with my partial fractions, 2 over s minus 1 minus 2 over s plus 1. Minus the inverse Laplace transform of, actually I don't need this big bracket yet. Instead of this, I have 2 over s minus 1 minus 2 over s plus 1. And now I'm allowed to take the two Laplace transforms, inverse Laplace transforms separately, and I can pull the 2's out. So I have e to the t minus 2 times the inverse Laplace transform of 1 over s minus 1 minus, this should be, subtract this whole thing, minus 2 times the inverse Laplace transform of 1 over s plus 1 . So when I replaced this term with these two terms, I had to put parentheses around it, so I'll remember to distribute this negative. Otherwise, it will come out wrong. Now, can you think of a function whose Laplace transform is 1 over s minus 1? E to the t again. So I have e to the t minus 2e to the t minus Laplace transform e to the minus t. So I have minus 2e to the minus t. Distribute my negative and combine like terms, and I have e to the t minus 2e to the t is negative e to the t plus 2e to the minus t. That's the function y of t that solves our differential equation and our initial value problem. No, but it can do more. Yeah, so we used a problem that we could have solved another way to start, but this technique can do more kinds of problems. I thought I left you a lot of room for that one.
You did, but there was one class ago where you didn't put any stuff room, so it was like this. I put a square around it. I went up here. There was
Okay, so that's how you do it. You try it.